The lecture assignment for today's lecture will be to take notes and do the example problems in your notebook. These will be your notes, so they can be as detailed or brief as you want, but you must take some notes. And you must do each of the example problems in your notebook. I will do each problem in the lecture so you can follow along. But if you are getting it or understanding what you need to do, go ahead and do them on your own, and you can always double check your answers in the back of the book. And then if you didn't do them right, you can come back to the lecture and review. So for this chapter, it's chemistry or chemical equations and reactions. We're going to describe chemical reactions, and we're going to use chemical equations to do this. So what is a chemical reaction? It's a process where one or more substances are changed into one or more different substances. So the substances that are going to go through the reaction are the reactants. The substances made are the products. In this example down here, we have sodium and chlorine are the reactants, and they will react together and make sodium chloride. So we have the word equation here, sodium and chlorine make sodium chloride, or yield sodium chloride, and then we have the symbols, Na and then Cl2 will yield 2NaCl. Cl2 is the diatomic molecules from last chapter. You should still have those marked on your periodic tables. In this example, copper is reacting with sulfur to make copper sulfide, and we have copper and copper sulfide, the product over here. These two are reacting. This is what is produced. So reactants and products. We represent this with chemical equations, and that's what you see right here. It's a representation of a chemical reaction using symbols and formulas to identify reactants and products and the relative molecular or molar amounts of each. So let's look at that amounts of each up here in our examples. In this here example, we have 1 mole of sodium, or 1 atom. Let's go with the atom first. 1 atom of sodium, 1 molecule of chlorine will make 2 molecules of sodium chloride. Remember the molar law we can use. The equivalent of 1 mole would equal what it is in atoms. So we can say 1 mole of sodium equals 1 mole of chlorine, which would equal 2 moles of sodium chloride. Same here, 1 mole plus 1 mole would make 1 mole. And those are two balanced equations. So when we're looking at whether a chemical reaction is taking place, we would look for physical indicators. First, the evolution of energy is heat and light, and sometimes energy is absorbed. So energy being absorbed or energy given off, but that isn't a single indicator of a chemical reaction because there are some physical changes that will produce heat. So we'd need another indicator or several indicators along with this one to definitely prove it's a chemical reaction. Color change. This one too is not in itself a chemical reaction indicator, but it is a possibility of one. So you have to look at this one with others. The production of gas. This is a good one. Anytime you have gases given off from a chemical reaction, it's a pretty good deal that it's a pretty sure thing that it's a chemical reaction. Formation of a precipitate. A precipitate is a solid that is produced as a result of a chemical reaction in solution. It will separate from the solution. I'm going to show you a video clip here of this first video clip of the chemical reaction of making a precipitate. So in this reaction, we're going to put lead nitrate and potassium iodide together. And as you can see, this is a new substance. So we've made a new substance, so it's a chemical reaction. And this substance here is not soluble in this solution, and you can see it's like the snow globe. This powder is going to settle out. If you let this sit long enough, the powder, this solid, will fall to the bottom, and you can see it's happening right there. So this is a precipitate. This second video here, we're going to do this one in class, and this is the reaction that takes place. And don't worry about what these symbols, don't write this down we'll go over this one in class, and when it copy and pasted, it didn't paste the symbols properly. So don't worry about that one. Don't write that one down. We'll do that one in class. The law of conservation of mass. We have to remember this law. Matter is neither created or destroyed. It only changes form. So when we're looking at chemical equations, they must represent known facts. So it must be a true chemical reaction that takes place. It also must contain the correct formulas for the reactants and products. Don't forget about the diatomic molecules. It must satisfy the law of conservation of mass. So in the end, we must balance it. To balance chemical equations, we're going to use coefficients. Coefficients are small whole numbers that appear in front of a formula in a chemical reaction. And like I said, we use them to balance them. So if we look at when we have a chemical reaction and what's actually taking place, we have to look at each atom that is in that chemical formula and how it's going to be rearranged and make new products on the other side. So methane, which is CH4 from a cow's butt, it is 1 carbon, so you can see the black here is the carbon, and then 4 hydrogen, 1, 2, 3, and then there's 1 in the back side, 4 hydrogen. It will chemically react with 2 oxygen molecules. Oxygen is diatomic, so they always form in 2s. So here's a molecule and here's a molecule. When they rearrange, the carbon is going to go with 2 of the oxygen molecules, and the hydrogen are going to go with the other oxygen molecules. So if you look at this and we count, we have 1, 2, 3, 4 hydrogen on this side, and 1, 2, 3, 4 hydrogen on this side. We have 1 carbon, 2 oxygen, 2 oxygen, so 4 total here, 1, 2, 3, 4 over here. That is representing a balanced chemical equation, showing with pictures, showing every atom, then with words right here, and then with our symbols, and then counting all the atoms at the bottom. And so this is what we're going to do in this chapter here. Balancing chemical equations, the fun stuff. So writing the word equation. Obviously, if you're writing the word equation, you're going to use words to describe the chemicals that are involved in the reaction. So the formulas aren't going to be made yet. The yield sign, you can still use the arrow, but if you put the word in there, you would say it forms this, yields, the reactants yield the products. Writing the formula equations, very important. Use correct symbols and formulas. Don't forget what we learned last chapter. So when we're balancing them, the first step is to write a correct formula for all of the reactants and products. Once you have that formula made, do not change any of those subscripts. Then you'll put a yield sign between the reactants and the products. Then you'll balance it using coefficients, which are the whole numbers in front of the formulas. You need to have the same number and kinds of atoms in the reactants and products. So you're going to add up the atoms of each kind on the reactants and the atoms in the products. And you're going to make sure that you have the same number on each side. And then the final step, double check. Always double check your work. Now there are other symbols that are in a correct and complete chemical formula. On page 252, there is a symbol chart. We're going to go through a few of these, but you need to go over that chart and look at the rest of them. States of matter. If we're going to have the state of matter involved, so if we're mixing gaseous oxygen with solid carbon, then we would have G beside the oxygen and S beside the carbon. Then an L, and usually this is a cursive L, and then aqueous, meaning it's dissolved in water, would be an AQ. There are other symbols, like I said, but those would go beside, and we'll do examples and show you what that would look like. Reversible reactions. This is a reaction where the products will reform the original reactant. So you'll have a double arrow. Let me write one of these. So we have our double arrow. So we have, whoops, that's not a very straight arrow. Terrible arrows, aren't they? You would have an arrow which would show going one way and then an arrow going the other way. There, a little better. So that's what a reversible reaction, the arrows would look like between those. So precipitate, another way to write, to indicate that a precipitate because the precipitate is going to fall out of solution or settle out of solution, you would have a down arrow beside the product that is a precipitate. And if it's a gas, you would have an up arrow because gases usually are lighter and they will go up. So those are some other symbols that we would use. Another symbol or another item that might be indicated in a chemical reaction would be a catalyst. This would be a substance that changes the rate of a chemical reaction but can be recovered unchanged. So the catalyst would be written over the arrow. So it's kind of a weird thing, but cigarette ash is a catalyst to burning sugar. It'll make sugar burn easier and at lower temperatures. So you would have the sugar, C6H12O6, or if you had sucrose, C12H22O11, and then you would have the arrow and you would put the cigarette ash, which there is a chemical in there that's doing it, but in this case, cigarette ash, and then it would have your products on the end. I don't know anybody who smokes, so I don't know where to get any ash from to do that, but we could try it. Coefficients, when we're looking at those coefficients, those whole numbers that are in front of the formulas, those are going to indicate the relative but not absolute amounts of reactants and products. They will show us the relative masses of the reactants and products because we know how much 1 mole of any substance is because of the periodic table. We can just look at it on the periodic table. And the reverse reaction for a chemical equation has the same relative amounts of substances as the forward reaction. Now these are the examples that we're going to do, and these are the examples that I would expect to have. I'm actually going to do these in a separate video so that I can use my iPad. So go to the video where we do the example problems for section 1.